the average farmer putting on to corn crop following beans? 150 to 200, right? So roughly 1.5 to 2% of the total nitrogen in the soil is coming from fertilizers. That's an important point there that we want you guys to remember by the end of the day here. So anybody know what this is a picture of? Yeah, an anhydrous plant. So this is an anhydrous plant. I don't know where it is, but great. Is this a? Oh, it's for the recording. Okay. Yes. Thanks. I thought it was remote. Nope. So, yeah, it's an anhydrous plant. So there's a new anhydrous plant going into southeast Iowa. For those of you that aren't aware, it's the biggest investment in Iowa infrastructure in the state's history. And they're retrofitting an anhydrous plant in northeast Iowa. So nitrogen fertilizer is here to stay. I'd like to call this the greatest invention in human history. And I'll show you why, right? So forget the TV, forget your iPhones, it's anhydrous ammonia. So here's a population curve from 1750 to roughly present. That's in the maroon. The green is a curve of Haber-Bosch ammonia synthesis, right? So this is the process that was invented a little bit before World War I by two German chemists at BASF. They won the Nobel Prize for their invention and subsequent industrialization of the process. So they pull nitrogen out of the air. The air is 78% nitrogen, right? We just can't use it, nor can corn and soybeans. And it turns it into ammonia fertilizer. And that's the green line there, right? So these two curves, the similarity between them, it's not coincident, it's not correlation, it's cause and effect, right? So without that nitrogen created from Haber-Bosch ammonia synthesis, we couldn't grow enough legumes on Earth to grow the human biomass on Earth. So roughly, anybody want to take a guess how much of the nitrogen in your bodies comes from that anhydrous ammonia plant that I showed earlier? 50%. 50%. Yeah, that's a pretty good guess. So in the developed world, I would say it's closer to 66%. Roughly about 2/3 of the nitrogen in your bodies came from an ammonia plant, right? So maybe make you feel a little bionic. And then in Africa, how many ammonia plants are there in Africa? I don't know, but I'm pretty sure it's close to 0. And so basically no ammonia there, right? And so we understand that there's consequences to that, and one is human health, right? So human health has been dramatically improved due to Haber-Bosch ammonia synthesis. This is why these guys invented the process and why they won the Nobel Prize for it, for its impacts on human health. And then, we're all here at the Iowa Water Conference, though, because there's negative impacts of this, too, right? So it's got really good impacts, really bad impacts. Anybody know where this is? This is in China at the 2012 Olympics, right before the rowing races, right? This is where they wanted to hold them. Not so convenient, right? Especially when you're on the world TV. By the way, anybody know about the average nitrogen application to a corn crop in China? It's over 300 kilograms per hectare, yeah. So roughly right around 300 pounds of nitrogen per acre. They're over-applying there because they don't have the education and extension system that Iowa's got, or the United States in general. And this stuff isn't easy to clean up, right? But we all know that, right? And then closer to home, of course, we've got the Gulf of Mexico hypoxic zone. I don't need to show this crap, but it's there, right? Another thing we've got to deal with. Even closer to home, the Des Moines Water Works, home to the world's largest nitrate removal facility. And if we're going to understand about how nitrogen cycles through these systems and what's the cause of those negative consequences, we got to think about a nitrogen budget, right? So you wouldn't try and operate your business or your household without thinking about a budget. And we got to do the same thing if we're going to improve nitrogen losses to the environment, right? We're going to keep more nitrogen in our crop system and reduce the losses to the environment. So here's a budget for an average corn system in Iowa. I want to draw your attention to that big green box on the left there. That's the soil organic nitrogen. On average, about 10,000 pounds of nitrogen per acre, at least on the Des Moines lobe down to the drains. So this nitrogen is largely insoluble. It's not easily lost to our waterways, right? So this nitrogen, it's held in the soil very well. But every year, when the soil warms up and gets wet, there's microbes that start to eat that nitrogen, right? They use it as food, they use it to build biomass, and then they have waste products, ammonia, right? Ammonium, just like we do in our waste. And then there's nitrifiers, and these are organisms that derive their energy from taking that ammonium, NH4, it looks a lot like methane, right, that we heat our houses with. So they're taking energy from that, and they're fueling their metabolism, and as a result, they release nitrate. And so we can count on them roughly to transform about 1 to 4% of that soil organic nitrogen to nitrate every year. So if there's about 10,000 pounds there, we can rely on about 100 to 400 pounds of nitrogen per acre per year from them. To put that into perspective, farmers are just putting on about 150 pounds of nitrogen per acre to a corn crop following soybeans, right? So it's important to consider these numbers related to one another. And then take a look at corn nitrate use, about 180 pounds of nitrogen per acre total use. And then about 115 pounds of nitrogen per acre per year in harvest. So that's roughly just a little bit over half a pound of nitrogen per bushel of corn these days that's coming off the field in Iowa, corn harvest. Then I want to highlight here nitrate leaching to waterways. On average, it's about 30 pounds of nitrogen in the form of nitrate per acre per year from a corn crop. So that's corn. What does soybeans look like, our other dominant crop in Iowa? Anybody want to take a guess on nitrate leaching from soybeans in Iowa? What's it look like compared to corn? So we don't, and most soybeans are getting 15 pounds of nitrogen and MAP or DAP every year, fertilizer in the fall, but generally people are not fertilizing soybeans. So what do you think the average nitrate loss from soybeans is in the state? It's the same. Yeah, that's right. So, no fertilizer on the soybeans, yet we're still losing on average about 30 pounds of nitrogen per acre per year of soybeans. Some folks are even starting to think that it actually may be higher in soybeans than it is in corn in Iowa. But certainly even in our long-term monitoring data from Iowa State. So again, in the same soybean budget, a couple of things to notice here. It's the same budget, but it's for soybeans. We can rely on those microbes again to mineralize a significant amount of that organic nitrogen that's insoluble and not available for crop uptake to nitrate, which of course the soybeans have to use quite a bit of, because if you notice there, they're just fixing from the atmosphere, the microbes that live in their roots are fixing about 150 pounds of nitrogen per acre per year, but we're harvesting well over that in grain, in soybean grain in Iowa. Anybody want to take a guess on the percent of nitrogen in soybean grain, or the pounds per bushel? So about a little over half a pound of nitrogen per bushel of corn. What do you think it might be for bushel of soybeans? It's over 3 pounds. It's about a little bit over 3¼ pounds of nitrogen per bushel of soybeans in Iowa. They're over 6% nitrogen, so a huge amount of nitrogen comes off in soybeans. Soybeans are big nitrogen users, and we harvest more nitrogen in soybean grain than we do corn grain from an average field in Iowa. And of course, the fixation isn't enough to account for that. So the rest of that nitrogen that the soybeans get is largely coming from the mineralization of organic matter. So how do we lose this 30 pounds of nitrogen per acre per year then? So what is the fact? It's the same in soybeans and corn. What does that tell you about nitrogen fertilizer? Big effect on nitrate leaching, fertilizer? Probably not so big of an effect if it's the same in corn or soybeans, right? So what does cause nitrate leaching from our waterways in Iowa? So this is a picture of a field in Iowa when we're losing a lot of nitrate. So it's at times a year like this, if it was 10 degrees warmer today. So when the soil is warm and wet, but there's no plant there to use the nitrate, that's when we lose it from the waterways. The soil's warm and wet. What drives microbial activity? Warm and wet conditions, right? Remember back to chemistry class in high school, the warmer and the wetter the conditions, the faster any reaction process happens, the faster the microbes work, the more nitrate released, and they're not doing it as a community service for your corn and soybeans, right? They're doing it to fuel their own metabolism. So if there's no plants to take it up, it gets lost from the soil and out to the waterways. And so this happens during times of the year when the soil's warm or wet and the crop's not, when there's no crop on the ground, or the crop is relatively young here and not growing rapidly. So for corn, it's really not taking up nitrate at a rate that's equal to the production of soil microbes until it's around hip height. So, you know, like V6 to V9 are those for you that know the corn growth stages, but about hip height. So here's a similar way to look at that. When is nitrate loss occurring during the year? So here we just have got a concept diagram, and on the x-axis here we have time, right? So the spring right now to the winter, March to February, and then we have the relative rates of processes on the y-axis. So the red, that indicates the relative rate of microbial nitrate production from the soil organic matter, and the green indicates the relative rate of corn or soybean nitrate demand. And you can see that mismatch in timing there. That mismatch in timing between the two curves is the reason why we lose most of the nitrate downstream in Iowa soils, right? So the biggest cause of nitrate levels, high nitrate levels in our waterways in the state, is the fact that we don't have crops growing on the soil for significant portions of the year when the soil is warm and wet, when microbes are creating nitrate from soil organic matter. That's the main cause there. So I like to use this figure here because we can think about what can we do, right? So I mentioned nitrogen fertilizer management, the 4 R's, right? The right rate, the right time, the right source, the right placement. Those are not going to solve our nitrate challenges in the state. They're not going to get us to that 45% reduction goal to the Gulf of Mexico. We're going to have to do more than that. We're going to have to address these times of the year when there's no crop growing on the soil, or we're going to have to put in engineering methods downstream to remove the nitrate after it's lost from the field. But I want to use cover crops here as an example of a strategy that works to keep nitrate in the soil because it addresses the root problem of the cause, right? That's a pun there, roots. No roots in the ground. So imagine the system, you know, fall comes along, it's time to harvest the crop. We fly a winter rye cover crop on, and it starts to grow. That's kind of depicted by that bright green line there. So it starts to grow in the fall, it gets rooted, it's taking up nitrate, it's avoiding some of that loss that would otherwise occur because the soil's warm and wet, but there's no crop there to use it. Now there is. And then it goes dormant in the winter. And then right around this time of year, maybe even a few weeks ago in the warm 2017, when the soil warms up and those microbes start to get active and create nitrate from the organic matter, that cover crop wakes up too and it starts to take up nitrate from the soil. And so the timing of the production of nitrate from the soil is well matched with the plant demand there. And as a result, we significantly reduce nitrate loss from the system. So to give you some rough numbers, the 4 R's, they may be able to get us, I don't know, 5 to 15% if we're really, really optimistic, reductions in nitrate loss from the system. In contrast, a well-managed cover crop could do well more than a 30% reduction in nitrate loss. A well-managed cover crop in the right crop system and the right part of the state could get us to that 45% goal. So, just want to summarize a few things here before we go on to the strategies we can take to reduce that nitrate loss from the system. So, an average soil contains 10,000 pounds of nitrogen. When the soil is warm and wet, microbes are transforming that nitrogen into nitrate. If there's no crop there to use it, we lose it. And so almost all the nitrate loss from Iowa crop systems goes to the waterways during times when crops aren't growing. So this is a pretty safe audience for no plant breeders. Sometimes I get in trouble when my plant breeder and genetics friends are in the audience. But people say, so what do you think we could do with nitrogen use efficient corn? 0. Right? Because the problem isn't that the corn's not nitrogen use efficient. Corn is really nitrogen use efficient. Look at the nitrate loads and concentrations in the waterways when corn is rapidly growing in July and August. They're 0. We're doing a great job of getting nitrate. The corn is doing a great job of taking the nitrate up when it's there. And then a couple other things I want to point out as examples that nitrogen fertilizer is not the main cause. There's really little nitrate loss from perennial plants. And I'll go into some examples here. But how much nitrate loss from an alfalfa crop in Iowa? Anybody want to take a shot? 0, right? Because it's a perennial plant. Just like rye, when the soil warms up and the microbes start producing nitrate, the alfalfa is already rooted in the soil and it starts to take it up. I'll go into that in more detail though. But here are some strategies we can take to reduce nitrate loss from the environment. So on the top, we like to break them into in-field practices and edge-of-field practices. So on the top, we've got these in-field practices. The nice thing about these practices is twofold. They keep nitrogen in the system, so they retain the nitrogen in your soil for future crops by avoiding loss from the system. The other nice thing about these practices is that they can be used anywhere, right? In any type of cropping system in general. And so on the left, we've got a winter rye cover crop, and on the right, we have diversified rotations. Hard to see, but that's just some alfalfa strategically targeted on the landscape. On the bottom here, we have what we would call edge-of-field practices. So these practices can only be used where we have tile drainage systems, but the nice thing about these practices is they don't take up a whole lot of acreage of corn production, and they're really, really effective. So here we divert the tile drains into a wetland or a bioreactor, which is being shown being installed on the right, and these denitrify. They rely on microbes again to remove that nitrate into nitrogen gas, which we're all surrounded by right now, right? So 78% of the atmosphere here is dinitrogen. These practices rely on microbes to take the nitrate after it's lost from the field and turn it back into that nitrogen. So essentially the microbes, instead of breathing oxygen, they breathe nitrate and they release N2 instead of CO2, moving it into the, back into the atmosphere. So here's just a concept figure for how the water pathways work. Because if we're going to think about avoiding nitrate losses or reducing them downstream, we've got to think about how the water flows to consider how we place these practices on the landscape. So on the left, we've got a naturally well-drained soil, and on the right, we've got soils with relatively poor drainage, right? So these have tiles in them, and here we can use both practices. So I want to highlight that, you know, a lot of literature suggests that soils with tiles lose more nitrate per acre, but certainly both systems are losing nitrate, and we have to address nitrate loss on both types of systems. We just can't rely on one or the other. Really, it's the pathway that's the main difference there. So why do we drain soils? Drainage is really important, right? So I like to say, you know, it'd be like western Kansas or western Nebraska. If we didn't have drainage, instead of being a desert, we'd be a swamp, and we wouldn't have all the nice infrastructure we have in Iowa State and all the wonderful people, right? So here we've got yields in Iowa, 1984 to 1986. So crop yields were corn yields were benefited by 10 to 45 bushels per acre back then. Soybeans 4 to 15. So think about what the average corn and soybean yields were back then. Those are huge increases in production. Anybody want to say, I know like 84 to 86, what was it, 120 bushels an acre maybe back then? So those were really big increases. So we need tile drains. Why don't we have good numbers for today? Because Iowa's relatively well tile drained, right? And they're hard to get. So just to review this, so we've got systems where we can use those edge-of-field practices, nitrogen management, land use, and then the systems without subsurface drainage, we have to rely on land use and nitrogen management to reduce nitrate losses. So here I want to go through Iowa's nutrient reduction strategy and some of the practices that we've listed here. So all these data come from the Iowa Nutrient Reduction Strategy, and these are practices that the Nutrient Reduction Strategy reviewed for their effectiveness on reducing nitrate loss from the system. So here we have 0 represents the current nitrate load, and that red dotted line represents the 42% load reduction that we're aiming for from corn and soybean fields in Iowa. And then we have sets of practices here. So the MRTN, that's not a good one. Let's go to nitropyrin. So that's a nitrification inhibitor. It inhibits that nitrification process. It's a chemical. So that would be nitropyrin treated fertilizer versus non-nitropyrin treated fertilizer. Fall versus spring, that's a very familiar one. Fall applied nitrogen fertilizer versus spring applied. So often people say, well, if we just applied all the fertilizer in the spring, we wouldn't have a problem. Well, we would still have a big problem because in the fall versus spring nitrogen, it's not even a guaranteed reduction. So those red bars represent the average reduction, and the black bars represent the standard deviation around that reduction. So what's that saying is that in many cases, Fall applied fertilizer loses less nitrate downstream than spring applied fertilizer, right? That's crazy to believe, but it just gets into the timing of precipitation which drives nitrate losses from the system. So I like to think about it like this. Nitrate loads and concentrations in Iowa waterways are high because of corn and soybeans. The variability around those high levels is due to the weather, right? Often the weather gets pegged for the high levels and concentrations. That's not the case. It's due to it causes the variability, which also causes the variability in the effectiveness of these practices. But from looking at these 4 R's, these fertilizer management, you can see that none of them are anywhere near sufficient to get to our 42% reduction goal. So here, if we start thinking about some of these other practices, so here is the rye cover crop. There you can see on average we get a 30% reduction, but again with a very large standard deviation. Some of those situations, cover crops is getting almost no reduction. In other cases, it's getting almost a 60% reduction in nitrate loss. What's causing that variability? So I think that variability we can manage, right? So we know cover crops are much more effective prior to a soybean crop than they are a corn crop because we can let them grow longer into the season for a variety of reasons. And then 2 years of alfalfa versus corn, this is the perenniality going on, right? So 2 years of alfalfa plus 3 years of corn, we have a 5-year rotation there, right? And we're comparing that to 5 years of corn. The 40% reduction that's coming from those 2 years of alfalfa is because there's a 100% reduction of nitrate loss in each of those 2 years of alfalfa. Over 5 years, that's 40% reduction loss. So the nitrate loss from the corn years in that corn alfalfa rotation is very similar to the continuous corn we're comparing it to. That 40% reduction is coming, 100% of that's coming from that perennial crop there largely. And then finally, we have these edge of field practices. And you can see up there, those are clearly the most effective and the type of practices that can get us to our nitrate loss reduction goals, right? Saturated buffers, bioreactors, wetlands, drainage management may be a little bit less effective, but certainly the saturated buffers, the bioreactors, and the wetlands. These are the things that will get us towards our goal without really throwing a wrench in production in the environment. And so if we think about those, we want to think about what would it take if we think about putting suites of those practices on the landscape. So certainly one practice is going to be more effective than in another area. The best example I showed is that some of these non-tiled acres, you just can't use the edge of field practices, right? So what do? They still lose nitrate. Well, maybe you use a cover crop. Maybe a cover crop, though, isn't really effective in Mason City, Iowa, because it's really cold and the soils are really wet, and there's a lot of continuous corn up there. It's just not going to be a place where a cover crop's ever going to work. But it's a great place to put an edge of field practice because all those fields are heavily tiled. So thinking about these suites of practices, these aren't suggestions, these are just examples from the Iowa nutrient reduction strategy. To get to that 42% reduction, we would have to take all the acres of corn, get them at the maximum return to nitrogen rate, that's the university recommendation, fertilizer rate. All the corn and bean and continuous corn acres would have to have a cover crop. Anybody want to take a guess at the percent of continuous corn and soybean acres with a cover crop in Iowa right now? What is it, Sarah? You just wrote a report on this.
Well, total acres is 2.6%. Of that, 60% is corn and continuous corn.
So of all corn and soybean acres, though, not even 5%. Yeah, not even 5%, right? So we're nowhere close to that, right? That would take a monumental change that would take longer probably than I'm going to be around. Then we've got the edge of field practices. 27% of all ag land treated with a wetland and 60% of all subsurface drain land with a bioreactor. How many bioreactors are there in the state right now? 10, 15? I don't think it's more than 100 or 200, right? And there's no way it's more than 200. And it's probably close to less than 100. And the wetlands, I don't know the number of those offhand, but not a whole lot, right? Here's just another example. The main difference here is there's fewer cover crop acres, but here we have the land use change. So 25% of the corn and soybean acres go into that corn, alfalfa rotation that I showed. That's a lot of alfalfa. Anybody know how we got that number? Did we just pull it out of the air? No, we actually put some thought into that alfalfa number. We took the highest acreage of alfalfa in the state's history, and that's where we got the number. Anybody want to take a guess on the year of that? It was in the 50s, I think, if I remember correctly. Late 50s, early 60s. And you know, we had a lot of horses back then, and not a lot of horsepower. And so that's the main factor affecting us there. So real quickly here, I just want to go into some of the cover crop timing, you know, finding a practice that works. Here's an example of simulating cover crop biomass production, which is a good proxy for its effectiveness at retaining nitrogen in the system. And we have 3 scenarios on the left where we plant it at 3 different dates: September 1, October 1, or November 1, and we terminate it all on April 25th. And you can see what a difference, just what a short difference in production, in growth creates. And the reason for this, just these short differences in termination or growing season of a cover crop makes a huge difference, because in the fall, growing degree days are declining exponentially, right? You don't get the same growth on November 1 as you do on November 2nd. You get a lot more on November 1 than November 2nd because on average it's warmer, right? Same thing happens in the spring. If you terminate it a week later, it's not a linear increase. You get a lot more nitrogen retention in that extra week than you did the prior week before, because growing degree days are accumulating exponentially in the spring. So really important to keep that cover crop around for a while. And then just finally, how long to measure a reduction, right? So I want to show this to this Iowa Water Conference. This is an important point here. How long is it going to take to measure a reduction at the Des Moines Water Works, right? A place where Iowans are really going to recognize this reduction. And so here is the nitrate concentration in the Des Moines, or the load at the Des Moines River, at the Des Moines Water Works, from about 1985 to present. If I just show you 5-year running averages, what does it look like there? It's increasing a lot, right? Whoa, we better watch out. It's in a big increase. But I could just show you another 5 years, and whoa, we're making major improvements, right? We're really doing our job. This is fantastic. But you look at the whole record. These are the 5-year running averages after the concentration stopped increasing at about 1985. We've been at about static levels at the Des Moines Water Works and load since about 1985. These are the 5-year running average loads, and you can see that there's not much difference. This is the actual loads that the 5-year running averages come from. And so what might it take to get a reduction? So if we're thinking about measuring a reduction, we have to think about the load in the background, in the context of the variability around that. Right, so that's the average with the standard deviation around it. And so if we want that 42% reduction, this is what it could look like. So the random weather variability causes that variability in load, as I mentioned, and you can see the average. And so these are all the potential scenarios over a 42% reduction in the next 15 years. And that looks really good. But how many people think we're going to make a 42% reduction in 15 years? No? Nobody wants to bet on that? Okay. How about a 15% reduction over the next 15 years? That's more reasonable, right? But even what this data says is even if we had a real 15% reduction over 15 years, based on the random draw of weather variability, we could actually measure an increase over that 15-year period, just on chance alone, right? This is called a Monte Carlo analysis, where we just simulate the random chance of things happening. It's basically like a card game. A good analogy I like to use is if the average weight of a baby in Ames is 7 pounds and we have one baby born for the next 5 days and we go from 7 to 6.5 to 6 to 5, would you conclude that the average weight of babies in Iowa is declining? Well, of course not. It's the random draw of the babies being born, right? So we just need to think about what's realistic here in the background when we start thinking about what kind of timelines we have. And so with that, I'd be happy to take any questions. Thanks for your time, guys. Yeah?
Have any of your genetics friends developed a clover that doesn't get over 20 centimeters tall?
Well, so that's a great point. The question is, have any of my genetics friends developed a clover that doesn't get over 20 centimeters tall? And so I am going to address that question indirectly. But a great way that the geneticists could help us out with the nutrient reduction strategy is to start investing in breeding of cover crops, right? Monsanto, Syngenta, Pioneer, how much money do they invest in breeding cover crops? Zero, right? It doesn't pay. This is the place where the government's got to step in and help us out, right? These are the types of things that we could really benefit from. Any other questions? No? Yeah?
Are you showing after soybean, how much of a release is that soybean plant throw off after harvest?
So how much release of nitrogen does the soybean plant give off after harvest? Zero. So soybean's a net user of nitrogen from the system. So by that definition, it can't release nitrogen into the system. And really, so where's the soybean nitrogen credit coming from, right? And so we can get, to provide some background for everybody in the room on that, the fertilizer required for an optimum yield of corn following corn is roughly 200 pounds of nitrogen per acre. The optimum fertilizer input for corn following beans is about 150 pounds of nitrogen per acre, so about 75% of that. And the actual yield and nitrogen uptake in the corn following beans is higher. So you're getting more corn with less fertilizer. How do you do that? For years we explained that as a soybean nitrogen credit. Soybean's a fixer of nitrogen, it brings nitrogen into the field, it leaves it behind for the next corn crop so you can get away with applying less. That's not true. So have you ever looked at a soybean field and a corn field after harvest? What's the difference? You can see the soil in the soybean field, right? And thinking about water, we've been learning about this for decades from an erosion perspective, right? But what does that do for those microbes that rely on warm and wet conditions in the spring? Well, it can't be too wet for them, and they like it really warm. In the spring, and the soil warms up in that soybean stubble faster. There's not the corn residue with a high C to N ratio to suck up the nitrogen, and there's more available. So it's really mineralization dynamics in the soil that are driven by microbes, not a credit.
So you say basically more trash.
More trash, yeah. So trash is another word for crop residue. Another good example of this is if you grow continuous corn and you harvest 100% of your stover, you can reduce your fertilizer rate. Same principle, yeah.
Michael, thank you so much.
Thanks, Sean.